given big Y n minus first derivative at x naught. Okay. Let me put, all this right-hand side stuff is given. Right? Just be dot, 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 dot. This is all given. The right-hand side is known. Okay. Now I'm just going to talk. Okay? What is this now? Okay? All these numbers now, y1 of x naught, those are numbers, right? 5, 3, minus, right? All the things with y prime of x naught. Those are numbers. The right-hand side is a number. What do I have at the end? I got something C1, something C2, something Cn equals a known number, right? What's the next equation? Something C1, it's n equations, then unknowns, right? And again, if you didn't have linear algebra, don't worry about it, but those who had linear algebra, see now that we have an inhomogeneous set of linear equations on the C's, and from linear algebra we know that has a unique solution provided the determinant is not equal to 0. But look at that determinant, it should look familiar. Isn't that just a Wronskian of x naught? Okay? So therefore we know, because the fundamental solution set by definition were linearly independent, we know that the coefficient matrix, when we write this as n equations and unknowns for the C's, is non-singular. Therefore, it has a unique solution. So we can find the C's. Okay? So what we've proven, again, I don't hold responsible for the proofs on any of these things, but the essence, is really what you have to understand. Namely, that this kind of gives us almost like a roadmap of what is going to follow. When we want to solve at least the homogeneous equation of order n, okay, what we're going to have to do? We're going to have to basically come up with n independent solutions. It's not just to guess one solution. Oh, x squared is a solution. You got to have all the solutions. And we know that we proved from before that if it's an nth order linear equation, it has exactly n independent solutions. And that's what we call the fundamental solution set. Okay? But the big thing now is, okay, how do we get those independent solutions? Okay, and that's basically going to be covered not in the very next minute, but a little bit later on. But let's get a little practice with this, okay, just so you can see what goes on. Again, unfortunately, at this point in the game, I'm going to have to give you the solutions. But again, I guarantee you by the end of the course, you'll be able to get all this on your own. It won't require me to say, oh, this happens to be a solution, because that's the idea of the course, right? Okay, so all I'm doing now is examples illustrating these different theories that I just talked about. Let's look at the following example. I'm going to take a second order equation. Second derivative of y with respect to x, okay, minus 9y is equal to 0. Okay? That's a second order linear equation. Happens to have constant coefficients, right? From what we just learned, we know that I have to basically, the most general solution of that is a linear combination of what? Two independent solutions. Okay? Now, we don't have the machinery in place yet to get those, so I'm going to have to give you those two solutions. Okay? It comes out that one solution to this equation, y1 of x, is e to the 3x. And the other solution, the second independent solution, y sub 2 of x, is equal to e to the minus 3x. Okay, let's verify at least the first one, okay? E to the 3x, okay? Well, if y is equal to e to the 3x, then the first derivative is 3e to the 3x, right? And the second derivative is just 9e to the 3x. And if I do the L operating on y in this case, I need a y double prime, which is 9e to the 3x, minus 9 times y, which is e to the 3x. That's 0, so it checks. And I leave it to you to do the same thing for e to the minus 3x. Plug that in, and you'll see that e to the minus 3x is also a solution. Okay, so I've got two solutions of the differential equation, two homogeneous solutions. Are those the fundamental solution set? I have to check one more thing. I have to make sure they're linearly independent. And that one you can see, one's not a multiple of the other. You don't need Wronskian for that, right? There's no way that e to the 3x in any interval is a multiple of e to the minus 3x. One graph goes like that, one graph goes the other way, right? So, e to the 3x and e to the minus 3x are both solutions of the homogeneous equation, right? They're linearly independent. So they're a fundamental solution set. So what does that say? From this we can conclude that the most general solution to to the equation y double prime minus 9y equals 0 is given by y equals some arbitrary constant e to the 3x plus another arbitrary constant e to the minus 3x. That's the most general solution. No one can come up with a solution that does not fall within that family, okay? Now, how would you get to C1 and C2? Well, if you had some initial data, right? If someone gave you y at 0, let's say, and dy dx at 0, you could solve for C1 and C2, just like we did in that proof over there, okay? So if one is given this problem, say on the exam, say, find the general solution to this equation, this would be the answer. For initial value problem, it may say, solve this differential equation subject to the following initial conditions. I don't know, y of 1 is 8, dy dx of 1 is 0, something like that, right? Then you would have no ambiguity in the c's, right? Because they'd be determined, okay? And this also agrees with something that we said before, that we expected in general, and, from the very beginning, that if you had an nth order differential equation, there would be n constants of integration or n parameters entering into it. And again, it makes sense upon any physical problem like you do. I remind you again of Newton's law, right? That's a second order equation. Instead of having y versus x, maybe it's y versus t, where t is time. Who cares about x versus t? Again, you gotta get used to those different variable names, right? And we know at t equal to 0, you need the particle's position and velocity. That's all you need to get a unique solution. If it was a beam equation, as I showed you before, that's a fourth order equation, and you need 4 conditions to get a unique solution. Okay? So it's very nice how the mathematics and the physics are going to complement one another. Okay? One thing that I always like to emphasize. So any question on this? Okay, again, all I did is I recognized it's a second order linear equation, okay? And I know from the theory that there can be at most 2 independent solutions. And here they are. We demonstrated that, okay? And the most general solution is always a linear combination of your fundamental solution set. And again, I remind you, the fundamental solution set isn't unique, okay? Maybe one guy wants to be kind of, funny about it. He says, okay, I'll take y1 to be e to 3x, and I'll take y2 to be 4 e to 3x minus 12 e to minus 3x, okay? Kind of silly, but you could do that because they're both fundamental solution sets, right? They satisfy the homogeneous equation, they're independent. And he could write C1 e to 3x plus C2 times the next one that I got. And at the end, he got the same solution that you had. It doesn't make a difference, okay? So again, all you have to do is come up with 2 independent solutions. And once you write a superposition, anyone else who comes up with what appears to be different fundamental solution set is really the same. Because when we start taking linear combinations, every fundamental solution set is really essentially the same. Okay? Just like with the ijk. If you want to use ijk, fine. If you want to use ij and k minus 3i plus 8j, same thing. Okay, another example. Okay. This goes kind of right for what I just said over here. Okay, let's do the same differential equation again. Y double prime minus 9y equals 0. Remember I said you guys are going to be smart aleck, you do something different? Okay, so e to 3x and e to minus 3x are solutions. Okay, how about this? Claim I can write the solution to that, a solution to that equation in the following form. 4 times the hyperbolic sine of 3x minus 5 e to the minus 3x. I claim that that's also a solution. Okay, I'm going to verify that. And then, if what I said before, I have to make sure I'm not lying to you, right? You should be able to write this guy as a linear combination of e to 3x and e to minus 3x. Okay. At first sight, it looks completely different, right? I see basically an e to the minus 3x in there. I got an e to the minus 3x. But now he has this hyperbolic sign, and I don't have that, okay? But the theorem says that the most general solution is this, okay? Therefore, even though it appears different on the surface, I'm going to show you that this is nothing more than this. And, just written a little differently. Let's verify at least. Does everybody remember what the hyperbolic sign is? I just kind of, again, I wouldn't expect you to remember this. The hyperbolic sign of z is defined to be e to the z minus e to minus z over 2. That's just, it comes out that in engineering, a lot of times you get solutions that are linear combinations of exponentials, like in, for example, a catenary, hanging cable, the solutions in terms of these hyperbolic functions. Okay, so it's just a shorthand notation for e to the z minus z over 2. And it comes out from the definition that the derivative of the hyperbolic sine is the hyperbolic cosine, and the derivative of hyperbolic cosine is hyperbolic sine. A little crazy because sine and cosine usually differentiate with a minus in there, right? Derivative of sine x is cos x, derivative of cosine is minus sine. But if you just use the definitions of the hyperbolic functions, I should put the other one down there to be complete. The cosh of z, that's e to the z plus e to the minus z over 2. You'll find the following, just by the definitions. You know how to differentiate exponentials. So you'll find that the derivative with respect to z of the hyperbolic sine of z is the hyperbolic cosine of z. And the derivative with respect to z of the hyperbolic cosine of z is hyperbolic sine. There's no sign change. Okay. Because we need that over here. Okay. So I verified in this case, example number 1, yes, that e to 3x and e to minus 3x both satisfy the homogeneous equation. Let's see if this is a solution to the homogeneous equation. Okay, because they claim that it is. Well, y prime is what? You use the chain rule again. Cosh times 3. I get 12 times the cosh of 3x using the chain rule, right? And then e to minus 3x, I get a negative 3 plus 15 e to minus 3x. Okay? Hope people are checking me, so I don't make a mistake. Okay, and then let's do one more derivative over here. Cosh is sine of 3 again. It's a 36 times the hyperbolic sine of 3x. And I guess I pick up a minus 45, right? E to the minus 3x. Okay, let's do L operating on y now. I need y double prime. There's that guy. I get 36 times the hyperbolic sine of 3x minus 45 e to the minus 3x, right? Minus 9 times y. What's we have over here? 4 times the hyperbolic sine of 3x minus 5 e to the minus 3x. Let's reduce in our head. Yeah, 36 hyperbolic sine minus 36 hyperbolic sine cancel. And the exponential minus 45 plus 45. Yes, it is 0. So that also is a solution. Yeah.
The hyperbolic stuff.
Yeah.
What class is that taught in? Because
you should be in your calculus book.
it was, but they skipped right over.
They
They're
didn't
like,
teach it.
we're not teaching it.
Okay. Okay.
Yeah.
I'm not going to hold you responsible for it, but basically, because what happens is that there's no real new mathematics, right? It's just a linear combination of these exponentials that you get, and you'll be able to do this yourself, right? Just if the class, just differentiate this. You know how to differentiate exponentials. You'll verify it. Okay. But you'll use it a lot is in things like take courses in civil engineering. You do things like bridges, cables, hanging cables, stuff like that. Okay. It's like I said, these were made up because that someone said, gee, I have nothing to do, so I'm going to call this combination of exponentials hyperbolic sine. It occurs so often, okay? That's why people give it a name and then they tabulate it and stuff like that. If you look in MATLAB or in Mathematica, they're built in, okay? Okay, so, okay, but the whole idea of this problem was to show you that, here's another solution, 4 hyperbolic sine 3x minus 5 minus 3x, I got that, okay? And again, if our theory is supposed to be solid, okay, it says that even though this looks different, it's really that. Let's do that, okay? What I'm going to do now is take this crazy solution that we just demonstrated and show you that it's actually this, basically, with certain c's, okay? Let's do that, okay. We do this over here, okay? What I'm going to do, basically, is replace what do I have to do? I think it becomes obvious, right? The original solution is in terms of an exponential. I'll leave that alone, because that's what I have over here. We have a hyperbolic sign. I'm going to replace that hyperbolic sign by its actual expansion in terms of exponentials, okay? And then see what we get. So the y over here, okay, is 4 times, what's the hyperbolic sign of 3x, just by definition? It's e to 3x minus e to the minus 3x divided by 2, right? That's the hyperbolic sign of 3x. Then I get minus 5 exponential of minus 3x. Okay, y is equal to 2 e to the 3x minus e to the minus 3x, right? Minus 5 e 3x. And now let's just combine all the exponentials together. I get 2e to the 3x. Then for an exponential minus 3x, I get negative 5, negative 2 is negative 7. Okay. And let's just go over here. Isn't that really that? It's the form C1 is 2, and C2 is negative 7. That's all. Okay? Now, many times what happens here, it was pretty obvious. Many times you'll, depending upon the technique that's used to solve the equation, you would get two solutions that look, you say, there's no way those guys are the same, right? And what, as a practicing engineer, what would I do first? Before going through all this mess and expanding, I would say, let me graph the two or evaluate them at certain numerical points, right? Right? If these guys are supposed to be the same for all x, then they have to agree at any value of x. So therefore, I just plug in x equals 0, x equals 1. Maybe I superimpose the graphs. And then once I see that, yeah, there's numerical evidence that indeed they're identical, then you can go through something like this. And again, this is rather easy to do. There are some things which I've done where actually it became a note in a technical journal because no one was able to prove it before that they were the same, okay? It can get rather involved, okay? Because many times there are identities involved. Imagine, see here there's no real identity that you have to do, but imagine someone wrote it and had cosecants and tan squared stuff like 1, and then you expand everything and say, gee, I don't see it, but maybe there's an trig identity that's buried in there that if you'd employed that, it would make it simpler, okay? And that happens in vibrations many times. When you do vibrations of things like plates or different types of continua, a beam or a plate, you get all these weird, oh, that's another place where hyperbolic functions occur. If you take an engineering vibration book and look up the solution of a vibrating beam, you'll see it's in terms of hyperbolic functions, okay? Okay, so doesn't mean you can't do it in terms of exponentials, but it's much more convenient, to do in terms of hyperbolic functions when you apply boundary conditions. Okay, so, but the important thing over here is that our theorem, is solid. Okay, yeah, you got an nth order differential equation. What you have to do is come up with n linearly independent solutions. Once you have that, you have the general solution by superposition. Okay? And any other solution is always expressible in that form. Okay. Okay, and you have another example.